We already had a brief discussion about photonic crystals in the third lecture while discussing electron and photon propagation through a periodic structure. In the case of photons, periodicity is in the dielectric constant or refractive index of the medium through which it propagates. We are going to have a detailed discussion in photonic crystals in this class. Photonic crystals are a class of nanomaterials in which alternating domains of higher and lower dielectric constants produce an ordered structure with periodicity of the order of wavelength of light. Since for an isotropic dielectric media, the permittivity is simply the square of the medium refractive index, another commonly used definition of photonic crystals is ordered nanostructures in which two media with different refractive indices are arranged in a periodic form. Notice, however, that this definition is not suitable for photonic crystals made from anisotropic constituents. Photonic crystals can be imagined as two interpenetrating domains, one domain of higher dielectric constant and another one of lower dielectric constant. They are called photonic crystals as they can affect the properties of photons in much the same way that ordinary semiconductor or conductor crystals affect the properties of electrons. Properties of electrons in ordinary crystals are affected by parameters like lattices and defects. In an analogous way, these types of photonic crystals can strongly influence the photon propagation. In a photonic crystal, for a certain range of energy of photons and certain wave vectors, light is not allowed to propagate through this medium. If we generate light inside, it cannot propagate in this direction. If we send light from outside, it gets reflected. Geometrically, photonic crystals can be split into three classes: one-dimensional, two-dimensional, and three-dimensional, as shown in these figures. In one-dimensional photonic crystal, periodic modulation of the permittivity occurs in one direction only, while in two other directions there are no change in the permittivity. Bragg grating is an example of such a photonic crystal, which is widely used as a distributed reflector in vertical cavity surface emitting lasers. Besides, such structures are widely used in anti-reflecting coatings, which allow to decrease dramatically the reflectance from the surface and are used to improve the quality of lenses, prisms, and other optical components. Two-dimensional photonic crystal possess periodicity of the permittivity along two directions like this one and this one, while in the third direction or in the vertical direction the medium is uniform. Examples of two-dimensional photonic crystals include photonic crystal fibers and periodically arranged system of dielectric rods in air. Three-dimensional photonic crystals has permittivity modulation along all three directions. The most known naturally formed three-dimensional photonic crystal is opal stone, which is well known for its unique optical properties. When turned around, it plays different colors. Because of such a behavior, ancient people believed that opal possesses some magical powers. Now we know that all these peculiarities are caused by the microstructure of opal. It consists of a number of microspheres placed at nodes of facented cubic lattice. Reflectance of such a structure strongly depends on the incidence angle of light. So when one turns it around, it starts to reflect light with a different wavelength. In the case of a large refractive index contrast defined by the ratio between N1 and N2, a complete band gap develops in the photonic crystal with a proper shape and proper crystal symmetry. In this case, the band gap is not dependent on the direction of the wave vector, which defines the light propagation. Also, the density of photon states goes to zero in the band gap region. So these materials with a complete band gap are often called photonic band gap materials. And it is a characteristic of such materials to have zero density of states in the photonic band gap region or for the frequency corresponding to the photonic band gap region. Similar to a semiconductor that cannot support electrons of energy lying in the electronic band gap, a photonic crystal cannot support photons lying in the photonic band gap. A complete photonic band gap is a range of frequencies in which there is no propagating solutions of Maxwell's equation exist. We know that in semiconductors, electrons get scattered by the rows of atoms in the lattice, which are typically separated by a few nanometers, and consequently an electronic band gap is formed. The resulting band structure can then be modified by doping. In a photonic crystal, light entering the material will reflect and refract off at the interfaces between the media. The complex pattern of overlapping beams will lead to cancellation of a band of wavelength in all directions, leading to the prevention of propagation of this band into the crystal. The resulting photonic band structure can be modified by creating defects in the otherwise perfectly periodic system. The effect of such a defect is the same as the defect introduction to the crystalline structure of a semiconductor. This means that new eigenstates appears inside the photonic band gap with energy corresponding to eigenfrequency of the defect. Thus, the radiation within the defect frequency will propagate inside the structure, or in case of multiple defects, the radiation will be guided like in a waveguide through these defect regions. For example, in one-dimensional photonic materials, an incident wave partially reflects off each layer of the structure. The reflected waves are in phase and they reinforce one another, and they combine with the incident wave to produce a standing wave that does not travel through the material. If the wavelength outside the band gap region enters the one-dimensional material, the reflected waves are out of phase and cancels out one another. Hence, light propagates through the material only slightly attenuated. Structures in which periodic domains of high refractive index close packed with the media of lower refractive index filling the void are called regular structure photonic crystals. Such a structure is also called an opal structure. In this case, band gap is not really a full gap because the density of photon state does not go to zero in the band gap region. One needs an inverse structure with voids of high refractive index and packing units of low refractive index to develop a full band gap. One approach is to produce an inverse opal structure in which the packed spheres are hollow and the void is filled with a material of high refractive index. So it is just the negative of this kind of structure. One way to produce such structure is to use polystyrene sphere packing and then fill the void space with a high refractive index material. Then polystyrene is burned off to leave holes, which creates a large dielectric contrast. So such kinds of structures develop usually full photonic band gap. The band structure of a given photonic crystal defines its optical properties such as transmission, reflection, and angular dependence. Many methods for photonic band structure have been proposed, and these methods fall into two broad categories. One, the frequency domain techniques, where photon eigenvalue equation is solved to obtain the allowed photon states and their energies. The advantage provided by this method is that it directly provides the band structure. Second category is time domain techniques, which typically calculates the temporal evolution of the input electromagnetic field propagating through the crystal. Then the band structure is calculated by the Fourier transform of the time dependent field to the frequency domain.